Hi, today we'll begin our final presentation for this class project, which we have built a machine learning framework to enable quick and accurate mechanical performance predictions on magnetic elastic granular architectures. Magnetic elastic granular architectures assemble from multi-branch units with magnetic ends, offering reconfigurability that are often absent in the conventional monolithic magneto-elastic materials. While experimental studies have yielded valuable insights into mechanical properties, but they're often expensive and time-consuming. Conventionally, computational models are a powerful tool for elucidating the fundamental deformation mechanisms. A previous work by Yan and co-workers has focused on mechanical properties of single-component system. And here we use a code that also provided them with simulations of multi-component system, aim to enlarge the data space, which will be more suitable for machine learning work and across different intriguingly, I see different equilibrium configurations across different systems. The gray area shows the combination that expands, and the color area shows the combination that shrinks. Moreover, I conducted mechanical tests. I see different mechanical behavior across the various systems. They can be divided into four types. Here, we can see the different mechanical performance of different types of systems. For mechanical properties, we interpret strength and toughness. There are conventional trade-offs in materials. Here are some snapshots of different systems. In this machine learning framework, we have two goals. One, with given bodies and windings, we aim to classify the type system, and we also try to predict the stress and toughness of the resulting system. For the classification part, we consider three methods: random forest, decision tree, and Gaussian process classifier. For the decision tree, for each run, I trained a model with 100 trees, and I generated the prediction based on the test sets. I never told the resulting accuracy. The same procedure for the random forest. In this case, I use a no depth limit. Lastly, I use Gaussian process classifier. I tried a few kernels, and they gave me very similar results. Thus, we can conclude that the Gaussian process classifier is the best classifier in this case. I believe the reason is in this data set, we have some sharp corners. So the Gaussian process classifier is perfect for modeling the curved and wiggly boundaries. Next, I will present the strength and toughness of the binary system made of different lengths of Y and bar. I'll pass to my teammate for the neural network part.
I'm going to talk about the neural network we built to predict strength and toughness. Now, to make this work well, we used 6 important techniques. First, data standardization normalizes our inputs so training is stable. Batch norm speeds up the learning process, and dropout randomly turns off some neurons to prevent overfitting. Early stopping knows when to stop training, and weight decay keeps our model simple and generalizable. And inverse transformation converts our predictions back to real units. We ran 3 rounds optimizing weight, steps, and dropout. The weights proved to be the primary driver for performance, while 0.1 dropout was crucial for final excellence. Ultimately, strength reached 94% and toughness saw a massive 140% improvement, hitting 75%.
Following the classification, my part focuses on predicting strength and toughness. Our biggest challenge was the small dataset, only 163 samples, which initially caused severe overfitting. To solve this, I implemented physics-informed feature engineering. Instead of using raw inputs, I expanded features with polynomial and interaction terms. This allowed the model to learn complex nonlinear relationships that raw data couldn't capture. For the model architecture, we compared 3 approaches: optimized deep, residual, and ensemble networks. The optimized ensemble was the clear winner. By combining diverse pathways, it handled our small dataset much better than the single-path models. Looking at the results, the ensemble model achieved an impressive R-square of 0.95 for strength, allowing for highly precise predictions. However, predicting toughness was harder, with an R-square of about 0.69. We attribute this to the fact that toughness depends on chaotic crack propagation, which is inherently more difficult to predict than simple stress accumulation. To conclude our group's findings, Gaussian process classifier outperformed other models for this data with sharp edges. For neural network, width had the largest impact, followed by depth and dropout, but optimal dropout was critical for fine-tuning from 84% to 94% accuracy. Among the 3 model architectures tried, the best model is the optimized ensemble with feature engineering. It predicts strength very accurately, while the prediction of toughness is more moderate. Thank you for watching.